Okay, let me start sharing the screen. Give me a second, I just checked and it just jumped away. Oh, people still join, fantastic. Okay, so today I'm going to talk about how to come up with solvable lattice models. First of all, I want to say sorry for clickbait. Of course, that sounds like I have some, fantastic way of coming up with solvable lattice models. I have a couple of examples, and I really have a hope that it's going to work further. So sorry for the clickbait if you fell for that. The second thing, it's work in progress. So partially results are done. Some things are written, some things are not written yet, and some things are not done yet. So I'm working on that. Okay, let's go then. I'm Slava Naprienko. And first of all, I want to talk about the outline of the talk. My talk is going to have 4 parts. In the first part, I'm going to talk about spherical lattice model. This is some model that was introduced in 2009. And this is quite simple and very illustrative. So I want to use this model to give the sense of how to come up with solvable lattice models. Then I'm going to talk about the spherical Whittaker functions and the fact that spherical repeated twice is not a coincidence because the model is very tightly related to the spherical Whittaker function. The third part is going to be, okay, there is a theorem that these two are related, but the theorem is kind of ad hoc. So you know the model, and then you know the functions, and then you show that it is the same. But what if you don't know the model to begin with? How would you get one if you just start with an interesting function and you want to come up with a model? This is going to be the third part of my talk. Oh, yeah, I'm sorry, I didn't upload the notes on the website yet. I don't think it's going to be very convenient for me to do it now, so I'm going to upload them after the talk. I'm sorry for that. So this is the third part. Third file in the chat. I don't think that Zoom allows to do this. It does. Okay. It says that I can attach file only from Dropbox or Google Drive or anything like this.
Just try dragging the file into the chat window. Hopefully it will work.
My file is on iPad, and I need to send from iPad to my computer. I
okay,
think that.
Never mind. All right, fine.
Yeah, sorry. I'm sorry for that. Next time I'll try to upload them in time. So yeah, I'm continuing my outline. So the first 2 parts is just 2 pieces, then they're connected. I show how to get from one to another, even if you don't know another one. And the fourth one is closer to my actual results. It is how to come up with the colored lattice models, which were introduced quite recently, 2019. And they are more intricate, they are more complicated. And the fact that you can come up with them without guessing, this is what my talk is about. So the main takeaway, if there is only one thing that you want to take from the talk, and you can skip after that, is that you can start with some functions from the representation theory of p-adic groups. Then you can use some geometry to chop it into pieces. Then each piece you can describe combinatorically, and this combinatorial data could be realized as lattice models. So this is a long journey, but of course it's not as easy as just to come up with them. But on the other hand, you don't need to guess at any stage. So this is kind of the benefit of this approach, and it's very natural. Geometric pieces are very natural. You describe them combinatorically very naturally. So this is a very good streamline. And I've done it for 2 cases, for spherical and for Whittaker functions, and it worked. I got the spherical and colored lattice models, and I'm working on the symplectic case, and it also seems to be working. So my hope is that it's going to go further and further, and other things are going to work as well. So let me start with the first thing. I assume that people in general familiar with lattice models, so I'm going to be quite quick here. I'm considering the model that is given as follows. I have flow coming from the top, and then living on the right. my flow is selectively getting from certain edges at the top row. And my boundary conditions are basically defined just by the top. I have only top boundary. It is where my flow goes. So let me show you here. Here I have that my flow starts at 0, at 1, and at 3. And here I have my partition, so my strictly dominant partition. So this is my model. And in my model, I allow only 6 following vertices. This model is called 6-vertex model. So basically, these restrictions say that my flow goes from the top to the right, and they don't touch by elbows. They either cross or they don't cross at all. And there is nothing when one touches another and another one kind of goes on the side. So moreover, for each of the vertices, I assign the following weights. So for type A1, the names of the types are historical. They don't mean that much. We have the i's are spectral parameters. So they actually depend on the row, which is typical in this kind of things. And there is a fantastic theorem in 2009 by Ben, Dan, and Solomon that if you write the top row as the sum of lambda and rho, you can do it because it's strictly dominant. In other words, it is just defined by another partition. Then the partition function is given explicitly as the following product of the deformed well denominator and the Schur polynomial. So I want to stay here for a moment and look at this formula because I like it. And this formula is quite interesting because this formula says that we can get Schur polynomial, which is already an interesting function, times deformed well denominator. Let me remind you that usual well denominator for the GLN is going to be just the difference of Zi, Zj, but here we have our term Q, so I think about this as deformed well denominator, and I have the product of deformed well denominator and the Schur polynomial basically as the partition function of a model. And this is a great result. And let me actually show you an example. I even decided to make an example because it's really nice. You see that it is not very abstract. You can actually do that. So let me just take lambda to 0. So I'm just taking specific lambda, and rho, it is just the decrease, and it is just a wave vector. I have it as 1, 0. Then my top boundary condition is 3, 0, and this is my model. In my model, I just have 2 rows. I have 4 columns. I number them from right to left, 0, 1, 2, 3, and I put my stream at 0 and at 3. Here you can see all the possible configurations that could happen. So let me go through them quickly. So if this flow at 0 goes down, then by the restrictions, I have no choice, but my first flow should go right away on the right. So we just define this thing. If this goes right away on the right, then for the second flow, I just choose when it's going to go down. It either goes down on the here, it either goes down here, or it goes down right away. And this is all the possible states. So I think that example is the best way to understand something. So this is a small example to get the fill-in. And now, according to the table, I consult the table above. I write the weight for each of the states. So here we have that in the first row, we have 2 horizontal types and 1 intersection. So again, I'm going to get Z1, 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 etc., etc. And the magic happens that if I add all these things, absolutely, I don't know, unexpectedly, they factors out, and we have this product of, let me use 2 colors. We have this product of the deformed well denominator, and we have the Schur polynomial, which is exactly the Schur polynomial for the lambda. For lambda for us is 2, 0. This is exactly the Schur polynomial. So, things just worked out. So I just wanted to show the example to see that, to show that it's actually very tangible. So, of course, you could say that it is nice, but so what? Yeah, some partition function does some, the partition function of some model does some result. But what is interesting about this particular model is that this value that we obtained is actually a value of the matrix coefficient from the representation theory of p-adic groups of GLN. And this is quite surprising because this is a very simple, specific mechanical statistics solvable lattice model, and it somehow gives the very exact value from the p-adic representations. So that's why I go to the second part of my talk. But before that, are there any questions about this fantastic model? I expected that because this is really nice and this is really great. Okay, so now I want to talk about spherical Whittaker functions. And I'm actually not going to talk about them that much. I'm going to use the black box, but I need some notation. And the entire slide here, it is notation. And don't be afraid. It is just very standard notation. So what I have, my group is GLN over non-Archimedean local field. You can think of p-adic numbers. I have the standard Borel group, which is just upper triangle matrices. I have the standard unipotent radical, which is upper triangle matrices with ones on the diagonal. I have the opposite ones, which is just lower triangle instead of upper triangular. For my field, I have the ring of integers. This is my maximal ideal in my ring of integers, and this is uniformizer, so very standard. I also have the diagonal, which I denote by T. I have the Weyl group, which is the quotient of normalizer of my torus over torus. And here it's going to be just the permutation group. And I can also choose the representatives to be permutation matrices. So in my head, whenever I write an element of the Weyl group, I think about permutation matrix freedom. It's not going to matter for us which representative we're going to take because everything's going to be compact invariant. So I have the maximal compact subgroup, which is basically just integer points of my group. So it is just invertible matrices where entries lie in the ring of integers. And I also need to have some information about the roots. So I realize roots as the pair of numbers. And as usual, I take the positive roots to be the pairs where I is smaller than j. This is quite standard. There are n of them, where n is the n times n plus 1 over 2. This is the cardinality of positive roots. I'm going to need this number in 2 times during my talk, but still. And just for convenience, when actually it is, it has a better reasons for that, but here it's just for convenience. I'm going to denote the diagonal for a given partition. I'm going to denote the diagonal element by pi to lambda, where pi, I remind you, is uniformizer. So this is just notation. There was nothing interesting happening right now, but I need all this notation. Okay, so let's go further.
Sorry, Slava, it's n times n minus 1 over 2.
Oh, yeah, I usually work with r plus 1. Sorry. N minus 1 over 2. Okay, yeah, thank you so much. Okay, so now I had a choice when I was preparing the talk. I had a choice. Should I talk about the representation theory? And I decided no. The purpose of my talk is to show how you can, by the rails, by the streamline argument, get models. And I didn't want to dwell into the representation theory that much. That's why I'm going to use the black box. So let's just pick some character on the opposite unipotent radical. I remind you that it is just lower triangle matrices with ones on the diagonal. And I have some character which basically takes the element, the product of the characters of the elements that lie below the main diagonal. This is very standard, but I just decided to write down so everything is quite explicit. And out of my black box, not explaining whatsoever anything at all, I define the spherical Whittaker function to be the following integral. This is a function on my group G. This is functional. And it is just defined by this integral. There is a very good explanation what it is, but I decided not to give it because it is not in the purpose of my talk. So let's just have a closer look at this integral, because if you just pull out of the integral to someone, there is no chance that it's easy to understand. So what's happening here? I integrate over my unipotent opposite unipotent radical some function and the character. So in my head, and it's important for my talk, there's like two pieces in my integrand, some function and the character. The function is very easy. What the function does is it just basically captures the diagonal. If you feed it an element, by Iwasawa decomposition, you can write this as the Borel part times compact, and Borel you can write as the unipotent times the torus element times the compact. And basically, the function just captures the diagonal part. So this is just some sort of diagonal function taking the diagonal element. And I think about z as being fixed. So I think about that so much. I think that it's fixed that I even forget writing that later. So if you see sometimes I forget write fz, it's because I think it's fixed. Okay. And the second part is the character that I defined before. As the result, we're going to have some function on my group, and this function is very important. But again, I'm not going to talk about that. And there is this fantastic, truly remarkable, great result by Kassaman and Shalaika from 80s that this exact function that I just described you could be calculated explicitly. It is like as much as one can hope. You can calculate this explicitly. If your element lies by Iwasawa decomposition, if the diagonal of your element is given by dominant partition, then it is some quantity, which is interesting. But if the diagonal is not dominant, then it's zero. So we actually very explicitly describe the values of the spherical Whittaker function. What is great, and why I'm talking about that, is that when the value is non-trivial, every time when you see orange, this is important parts in my talk. When the value is non-trivial, it is exactly the value of the partition function that I described in the first part of my talk. So the formula that Kassaman and Shalaika yields is actually the same partition function that we got in the first part of our talk. So it is actually the same quantities. Yeah, and I write here, in other words, the partition function gives the values of spherical Whittaker function. So and there is a bit of shift, don't think about that. So, but basically they're almost the same. They're the same. Just like, let's say that they are the same. And the usual proof that in the style of the proof that Henrik told us 2 weeks ago is how do we understand that there is partition function and there is some matrix coefficient, or there is solvable lattice model, there is some matrix coefficient. How do we show that it is the same? The usual proof is we show that the lattice model satisfies some Jan-Baxter equations, which is just some functional equations. On the other hand, on the p-adic side, we have certain intertwining operators, and then we see that they change our functions in the same way, and then we have the base level. This is something that Henrik was talking about 2 weeks ago, so I don't want to, and it's not important in my talk as well. I'm just talking about some proofs that are standard now. But these proofs require you to have already the partition function. And then you show that if you do certain things with both sides, when you have already solvable lattice model, then you work on both sides and then you get the equality. Okay, so let me give a brief overview. So we have the spherical Whittaker function. This is just some very explicit model with a top boundary condition. With this choice of weights, the partition function of my model gives exactly the values of spherical Whittaker function from p-adic side. This is a little example. This is my function. I just define it as the integral for the purpose of my talk. And there is standard proofs now how to show that they're the same. But what is important for me, at least in this talk, is what if I don't know the model? And this is not a silly question. For example, if you do the very same thing for symplectic group instead of GLN, it is actually quite hard to come up with a lattice model. And it was done fairly recently. But if you do it for orthogonal group, then it's even harder. And to get the very same result by Kassaman and Shalaika, certain product of deformed value denominator times the Schur polynomial, to get it as the partition function of solvable lattice model is actually quite a problem. some people were thinking about it, and it seems like it's still quite hard, and you don't know exactly how to come up with a model. So this is, a real problem. This is how I started to do these sort of things in the first place. I was trying to come up with a model for type B for orthogonal groups, but I couldn't. So probably, that I'm just still exploring these questions. So the third part of my talk is alternative approach, how you could start with the Whittaker function and nevertheless write it as the partition function, in some sense not knowing what the lattice model is going to be. But before I go to the third part, are there any questions? That's great. It's very good pace. Okay. So I go to the third part of my talk, how to come up with spherical lattice model. So let's concentrate on this great example, which is very clear. Everything is very explicit. So the first page that you see on the screen is somewhat boring. So if you get bored, it's natural. The next page is going to be more interesting. In the first page here, I just want to simplify the expression and get the essence. What I mean by that is that originally my function is defined on the entire GLN, but by the way how it's defined by this integral, actually it's kind of left invariant, right invariant by compact subgroup, and on the left it's kind of invariant by the unipotent radical. So in reality, the only thing that I need is the diagonal part. So I can just do some simplifications before I go to study that. And so basically, I'm kind of skipping this here. But if you just, this is Haar measure of my unipotent radical. So, you just do the changes. You remember that F doesn't fill K on the right. No matter what K here, it's not going to affect the value. And it also doesn't fill U. So no matter what U is going to be, it also doesn't affect the value. So by making the change of variables, by making the by making change of variables, we basically get very predictable constants that are not interesting to us. Okay, so now it's enough to look at the diagonal part. If we look at the diagonal part, I'd make, again, some change of variables and basically isolate dependence on lambda into the character. This is the main part. I want to get away from my function f. My function f, I want to be simple. I want to get all the dependence into the character. Okay, this is basically what this page is about. I simplify my Whittaker function so that at the very end, it only depends on lambda, because it is only dependent on the diagonal element, and I just write it as parameterized by lambda. And my dependence on lambda, moreover, is localized into the character. This is some simplifications. Now, the next slide is interesting. Sorry for the boring one. Let's go to the interesting slide. There is a theorem by Peter McNamara that actually I'm going to give a moment here. The theorem is vastly more general. It's just I'm just given the most particular case you can even imagine of this theorem. The theorem is actually working for metaplastic covers, for arbitrary word decompositions and everything. I just take the smallest piece. So please don't think that this is it's actually shining, but I'm taking a very small piece of that. And so what the theorem states is that you can decompose the unipotent radical, the opposite U minus, into certain pieces. Okay? Each piece, my function f is constant on each of these pieces. And moreover, this decomposition into pieces is geometric in heart. Unfortunately, I don't have time to talk about the geometry here. I just want to briefly mention that these pieces, they're in one-to-one bijection with Mirkovich-Vilonen cycles. And the cycles are used to parameterize the basis of the intersection cohomology of the affine Grassmannian. So it is highly geometric data, and they are bijectively corresponding to this data. So there is actually some geometry happening, but for the purpose of my talk, I don't want to talk about that. We can think about this as just, I'm taking unipotent radical for GLN, which is very particular matrices, and I just separate them into small pieces. Now, of course, if I decompose my domain of integration into pieces, I can just write my function, which is defined by this integral. I write it into the pieces. Now my function f is constant on each of these pieces. So my constant just go away, and I just denote by g lambda m this integrals over these cycles, over the cells. This CMs I call McNamara cells, and my expression becomes, you already here start to feel that something could be combinatorial. Originally, we started with some integral of the unipotent radical, but here we already see that we decomposed something into pieces parameterized by certain numbers, and we already start to feel that we have at least some sum. So we start to feel that there is some combinatorial filaments start to appear, and our intuition works because for almost all m, my integrals is 0. There is actually only a finite non-trivial piece of all the possible m's where my integrals are not 0. And this data is usually called Lutstick data. And I'm not going to explain what it is, but name dropping. I just say that there is a way to look to see that this sum is actually finite. So let me review again. We start with the integral, decompose the domain. We have infinitely many pieces per se, at least at first, but then we show that almost all of them are actually 0. And now the punchline. Each of the state in the spherical lattice model correspond to each non-trivial piece. And moreover, the weight of the lattice model is exactly the value of the integral. So you see, we started from the integral, we decompose something into geometric pieces, the domain of integration. We look at the things that give non-trivial contribution, and each of these geometric subvarieties of my unipotent radical, they correspond exactly to the states in my spherical lattice model. Moreover, integral, the value of the integral, are actually exactly the weights of my states. And of course, if I sum them, I get the partition function. So this is the main punchline here of the spherical model, at least. So, but at the moment, I'm telling you, yeah, then reminds me that the Lutstick data and this finite the finite set that I'm talking about is the parameterization of crystal lambda plus rho. There is crystal basis. This is combinatorial analog of the representations of groups. Yeah, Lutstick data is parameterized and basis. Yeah, it has weight representation. I just wanted to kind of that video. Sorry, Ben. So I just wanted to actually the next slide is exactly about that. Next page. I just wanted to not concentrate too much on Lutstick data. Again, you see, I skip everything that is not helping you to come up with lattice models. So I'm really trying to be practical here. But yeah, of course, it is parameterizing some colored crystal or some crystals, which is fantastic combinatorial data, which is very similar to representations in Howard. So this is the main punchline. But at the moment, I showed you some Lutstick data, and I didn't describe what it is, so you could think, yeah, there is some Lutstick data. You have no idea what it is. So let me make things more real by the following bijection. There is a bijection between Lutstick data and Gelfand-Settling patterns. And Gelfand-Settling patterns are very easy to describe. And I think, again, my strategy is describe everything on examples. That's the only way how I understand things, and I hope it's true for you too. What is Gelfand-Settling patterns? This lambda plus rho is going to be my top row. Okay. Now I consider triangles of numbers with the following betweenness condition. If I look at this, in Russian called zigzag, I don't know how to say in English, let's say W's, then we see that they are non-strictly decreasing. In other words, for each entry lies between two entries above. If you look at any entry, for example, here it's 2 lies between 3 and 1. And it's true for each entry. Okay, let me finish with the bottom one. So if you look by these shapes, they all non-strictly decreasing. And if you look at all the possible sets like this with the top row 3, 1, 0, it's going to be there in bijection with Lutstick data corresponding to 3, 1, 0. In other words, okay, sorry for that. I didn't explain you what loot-stick data is, and I'm not going to. But I say that it's bijective to the Gelfand settling patterns. Oh yeah, and I already reviewed. And there is a bijection between Gelfand settling patterns and state in our spherical lattice model. And let me describe it. If I have some pattern with top row 3, 1, 0, I say that my floor should go down at 3, 1, and 0. The second row tells me that only two streams go down, and they're gonna go down on 2 and at 0. And the last one's gonna go at 1. It might be not clear, but it's rather trivial that this data defines the path uniquely. And let me show you on this example. Let's start with the stream 3, with this one. I cannot go down because there is no vertical edge, so I doomed to go on the right. Now I cannot go on the right because otherwise we're going to have not admissible state. So I need to go down. From here, the only thing I can go to the right, then I go to the down, and then the only thing I can do is go to the right. So I'm doomed to do these things. Now let's go from the 1. If I go down, it's going to be a vertical edge that is not in the pattern. No, we cannot do this. We go on the right. Now, if I go from here to the bottom, then there's going to be a weird thing. So I go on the right. And when I start from 0, I go to the down, to the bottom and on the right. Okay? So this is the only state. So the state is uniquely determined by the pattern, Gelfand settling patterns, and there is bijection between them. So I didn't explain you what loot-stick data is, but whenever you hear loot-stick data, you can replace it by Gelfand settling patterns, and you'll be fine because there is bijection between them. Okay, and so what is happening here is that we have the states in our model that are in bijection with Gelfand settling patterns, that are in bijection with loot-stick data, and loot-stick data parameterizes these geometric pieces how we decomposed our Whittaker function. If we read this from the right side, this is the direction that I'm interested in. Let me use the red arrows. I start with my function. I geometrically decompose it into pieces. I combinatorically describe them in terms of loot-stick data or in terms of Gelfand settling patterns. And then I show that they basically could be realized as the model. This is the most sketchy part. And I'm going to actually go for that and not avoid it. When I'm talking about all these things, you might notice that I never talk about solvability. I never say Yang-Baxter equation. I never say intertwining operators. I never talk anything about that. And this is the feature of this approach, that this approach gives you the bijective correspondence between states and the geometric data parameterized by combinatorial data, but I never need any solvability to show this correspondence. And the good part about this approach is that I get all the weights without guessing them. Because all the weights, as I described earlier, this is going to be the weights. The weights are just p-adic integrals. So I just know what weights are. I know what weights are, and I know exactly how each vertex, what weight is going to carry. So actually, this is, when I started from the solvable lattice models and I was looking at the weights, they looked for me quite arbitrary. But at least in this model, weights are actually the p-adic integrals of a character. So it's quite surprising. That actually has some geometric meaning. And so this is the main streamline here. And what is the remark that I want to make is that the calculation in terms of loot-stick data is actually made quite uniform for any split reductive group, not only for GLN. So this part is already done. This part is morally done already. You can take symplectic group or orthogonal group, and you can write the values of the Whittaker functions in terms of the loot-stick data that correspond, in terms of loot-stick data corresponding to this type. So this part is done. The next part, Gelfand settling patterns. The Gelfand settling patterns for different types are also introduced. there are several versions. Probably the most useful one is by Proctor that we used in the only type beyond A. In type C, we have ICE lattice model for type C. And if you write it in terms of patterns, it's actually going to be Goffin settling patterns for type C, which are in turn Lutstick data. But you could, just get this model for free if you would start with symplectic group with a Whittaker function, and then you go on the left. And then you would go to the Goffin settling patterns. You could even come up with Goffin settling patterns without knowing them. This is non-trivial combinatorial object. And then you go to the states in the lattice model. So I was talking about that in this approach, there is no solvability. But actually, solvability now is not that hard to show, because I know that in my p-adic side, there are intertwining operators. So I know that if I use that intertwining operator on my p-adic side, I'm just going to get some functional equation between two values. On the other hand, I know that both of these values, they're actually written as this combinatorial sum. And I know how you multiply things and how, this is basically partition functions. In other words, I automatically get the train argument. If you attach the R matrix on the left, and then you go on the right, and then you get weight on the left and on the right, and it yields you the functional equation. This is the equation that you can get when you already come up with a model using this rails, using this train. How do you know that intertwiners respect to decomposition and to Lutstick data in general? Ben is asking very, very tricky questions. I chose the description into Lutstick data and the decomposition, but I never told you which one. There is a good one, and you can choose it. And there is good one for each type. So for arbitrary decomposition and for arbitrary Lutstick data and for arbitrary parameterization, it's not necessarily working. But there is a theory of Littleman on cons and patterns that there is always a good one, which basically corresponds to the branching rules. But unfortunately, I don't think that I have time. We can talk about that after the talk. So Ben knows the story. So Ben asks right questions, tricky questions. But I can talk about that at the end. So let me give a brief summary before going to the last part. So we start with spherical Whittaker function. Then it's given by integral. I decompose integral using McNamara's decomposition. Now, only for finite set of Lutstick data, which is in bijection with Goffin settling patterns, my integrals are non-zero. But now my Goffin settling patterns are in bijection with states, and I have this streamline argument. So this is kind of how it works. In practice, you would get to the Spartans. You know that intertwining operators for the Spartans going to give you some changes of values. So you are tiny step from the model. I'm actually thinking this is almost on the humorous side, but I was actually spending several hours trying to think that maybe there is some sort of Yang-Baxter equation you can attach to Goffin settling patterns without thinking about lattice model whatsoever. Maybe you could, I don't know, do something like this. But of course, it didn't quite work. But if you don't need to go to lattice models at all, maybe you could do lattice models right on the Goffin settling patterns. It would be funny, but it seems like it's better if you do the grid, because the grid has more structure and you can localize things. Oh, Ben has lots of fantastic comments, and I don't know some of the things that he's talking about. Maybe you can just do the solvable Goffin settling patterns. Then you don't need lattice models at all. then I need to finish end my seminar. But anyway, so yeah. So this is the summary. You start with the function, you decompose it into pieces. Only for finite set of pieces, it's non-trivial contribution, and you describe it combinatorically, and you get the states. Okay. Are there any questions before I go to the final part about the colored lattice models and my results?
So I have a quick question, Slava. Yeah, really interesting talk. But so once we get the states, how do we get the rectangular weights from this? Can you get the like, can you get the rectangular weights?
Yeah,
as well?
yeah. That's a fantastic question. Yeah, thank you. This is something that I'm not talking that much. Yeah, I decided to concentrate on the bijection rather than on the weights, because bijections seem to be easier to show, and weights going to be slightly more technical. But the punchline is these weights, they are actually the product of the positive roots of more elementary weights corresponding to each root. But now we have the natural parameterization of these roots. And if you look at the model, then actually this one's going to be the first root, the second root, the third root, etc. So actually each weight is localized. When you calculate the integral, your integral will just take the form of the product. And each entry in each term in the product is actually the rectangular weight of each of the vertices. So you actually localize. It's not like you take the state or the weight of the entire state. In the way of how you calculate the integral, you actually localize it into each vertex independently.
So which vertices contribute weights for you know, the different roots?
So basically, whenever we see that something goes down, these things are definitely gonna. Oh, there's someone else joining. So let me describe it slightly differently. Notice that we have, for example, here I can write the Gelfand settling patterns, which is 3, 1, 0, 2, 1, 1. This is the corresponding Gelfand settling pattern. But the ways how Gelfand settling patterns works, it is by branching rules. If you start with a character, then you decompose it into the rank -1 characters, and then you go like this up to the very end, up to GL1. And what is the punchline? Yeah, let me finish. What is the punchline is that the number of the elements here, it is exactly the number of roots. So this is the number of positive roots. So in other words, when you write your weight as the product of a positive roots, they correspond to each of the vertical going down places. And this is, let me show, okay. So we see that this is the first place where something goes down. This is the second place something goes down, and we see that these are the only weights that are gonna give the contribution. This is another place where something goes down, and this is going to be another place where something's going to give the contribution. And when we look at the weights, we see that when nothing happens, it gives us 1. So it doesn't give us any contribution. So weights are localized exactly in the places that correspond to the positive roots, and they go down. So it's a fantastic question, and indeed, when you calculate the integral, you get the localized weights. So you actually get the Boltzmann weights of each of the vertices. You don't get just the weight of the entire pattern, of the entire state. Yeah, thank you for asking. Okay. Yeah, there was another question. Yeah. Proctor has patterns for other types, but the problem is that if you want to start with a pattern, you don't know the weights. This is something that I was trying to do when I started to do this sort of business. I was thinking, I want to have lattice model for type B. I know that Proctor told me that there is patterns of type B. So let me try to write pattern of type B, but now I cannot come up with the right weights. What weight I should put on each of the entries so that it's going to be solvable. So it's going to give me exactly the value of the Whittaker function. I couldn't do that, and apparently it's quite a hard question. This is something that people call Takuyama formula. Takuyama combinatorial theory is when you describe the Kassuman-Shalaika formula in terms of the combinatorial data. For example, Gelfand settling patterns. It is a big topic, and it seems like orthogonal group is still very hard to attack. Okay. No, and that's to say, Valentin asks a similar question to what Ben asked earlier. I cannot do this for arbitrary, but I didn't mention you which decomposition I chose. I chose a good one. For the good one, everything works, and there is a good one for each of the types. But I cannot pick arbitrary decomposition and get solvable lattice model for arbitrary one. So it is limiting, but at the same time, it works. You can get a good one, and from the good one, the argument is streamlined. You put something on rails, and it just goes up to the end. But you cannot do this for, I take whatever I want.
Can you get a non-solvable model then?
This is funny question. This is somehow better question. What I can do, I didn't write it down, but what I can do if I pick not a good one, not a good decomposition. So imagine that here I have, okay, let me actually give a moment and explain what Valentin is asking. So basically you can pick another decomposition into cells. So here in this part, I didn't tell you how I decompose these things, but there are many ways. And I pick a good one. If you pick a bad one, it is not true that only finitely many integrals going to be non-zero, not going to give non-trivial contribution. Generally speaking, the third step is going to fail. Okay, so we don't have a chance of getting any sort of finite combinatorial formula. But what is true, nevertheless, is if you can describe, if you I mean, I didn't write it, so I feel a bit hesitant to talk because I don't have any finished proofs written. But it seems like when I was thinking about that despite you have infinitely many states this time, it is not finite. These states are classified in finitely many categories. You have like several arrays, and you have the infinitely many states through each of the arrays. So in fact, you can, for example, have sum over 5 arrays. Each of them is infinite family. So it is not solvability, but it is not arbitrary sum. It is some structure which is quite intrinsic, and it is not as beautiful. So I prioritize other things. But nevertheless, there is some sort of semi-solvability, quasi-solvability.
Okay, great, thank you.
Mm-hmm. Okay. Yeah, I have about 10-15 minutes. So what about colored models? They're way more complicated. You have crazy colors and everything. So let me show you what colored lattice models are. Now, instead of just having 6 vertices we had before, we have different colors. So when we think about the paths, we actually think that we start with a colored path that goes somewhere. If you think that this picture looks familiar, it is exactly the picture from the first part, but colored. But now, since my paths have colors, I have additional data. So it is more intrinsic, it is more refined version. Additional data is what is the permutation of incoming colors and what is the permutation of outcoming colors. I call it the input and the output. What is the permutations for the input and the output? So in this example, if this is how I number my colors, red, green, blue, sounds very natural to me, RGB. Then in the model that I show you here, the output permutation is basically the reflection of 2 and 3. It is cycle to 3. I think about this as the veil element for the reason I will explain later. And these kind of models, they were actually introduced quite recently in 2019 by Dan, Ben, Valentin, and Henrik, and on the other side by Alexei Borodin and Michael Wheeler. And so this is kind of, we're getting closer to something that is happening right now. And these models, the weights for them are way more subtle, because now you can have lots of crazy situations. For example, you can have intersections of colors which is higher or smaller that goes like this. They could touch elbows this time. Before we didn't allow this kind of things. So it could be honest intersection, or it could be intersections when they actually just touch the elbows and go further. They also could go through the same vertical edge. So the colors become, the weights become very hard. You actually need to do the fusion process. This is something that we had also in Henrik's talk. So this becomes way more subtle. But let me show you, before going to the technical part, show you, this is from my research. This is something that I was writing to myself. We have the colored loot stick data, colored Gelfand settling patterns, and colored lattice models. There is a very natural way how you can assign colors to the loot stick data, to the Gelfand settling patterns, such that the same bijections hold, and you again have the correspondence. I didn't explain anything yet, but you can at least see that it looks fantastic. It looks very plausible. So this is the way how it works here. So we can refine all 3 steps into the colored versions and get everything as before. I introduced colored Lustig data and colored Gelfand settling patterns as combinatorial objects. This is something that sits between the colored states and the geometric decomposition that I'm going to talk in a moment. So you see, this is quite interesting. At least I like it a lot. Whenever I see colors in my research, it doesn't seem so gloomy, and it's actually very nice looking. And I show my research to friends, and whenever there are colors, they think it's fun and nice. So let me go back to the final part of my talk. So this is the colored lattice model, way more subtle, and nevertheless, again, it is vulnerable to the attack of this method. What I'm talking about. Black box number 2. Again, I'm not going to explain what Iwahori-Whittaker functions are. I'm short on time. But what is happening is that now I have the, let me spend still at least some time. Now I define new functions. Before I had one spherical Iwahori function. Now I have functions that are parameterized by permutations. Okay? So now I have new functions. Function is very similarly given by the integral, but there is a little delta. You see that this is the only place where something is different. This little, this sigma is sigmas. And what has happened, what is the difference between usual f and f sigma is that f was capturing the diagonal. I was telling you that basically f is, give me the diagonal, I'm going to raise a z to this. But here, it depends on the Iwahori decomposition. So it is not just the diagonal. Depending on which double Iwahori coset we lie in, sometimes it is 0, or sometimes it is the diagonal. So this is a refinement. And it is strictly speaking the refinement. What I mean by that is some of these functions give us the previous one. So from here, we just strictly get the previous case. Because if you just literally take the sum of these f's, you get sum over all possible sigmas, and you get the previous function, which is going to be the diagonal. So this is just strict generalization of the previous approach. But what is true here is that if we look at the McNamara decomposition, it is not enough. Because before we had our function was constant on each of the pieces. This time it's not true anymore. Because this time we have 2 decomposition. Pay attention here. We have one decomposition into the McNamara cells and another decomposition into double Iwahori cosets, which I don't explain, but it is just a refinement of the decomposition. And since my function depends on the Iwahori decomposition, sorry that I get so sketchy in this place. This is Iwahori decomposition. Then I need to analyze the intersections of McNamara cells with the double Iwahori cosets. So this is a new geometric structure, which is a refinement of the previous one, the previous that Peter introduced. So they are subsets of the cells that we discussed before. And I go to the very last slide with my results. So first, I describe these intersections explicitly. And punchline is that each of these subcells, I call them subcells, each of these subcells, they correspond to a state in the colored lattice model. And its weight, integral over this subset, is exactly the weight over of the state. So again, the same as before, it again works. Moreover, the data is parameterized beautifully. What I mean by that M, let me use the red, M, as before, parameterizes kind of the backbone, where my pattern goes down, where it goes on the right. But this time, a new additional parameters, sigmas, they parameterize the input and the output.
Slava, are you missing a J in that theorem again?
In which one?
Is there a J between those two?
Oh, yeah, you're right. Oh. Yeah. yeah, I'm trying to describe this element, so I need to have J. Oop, good catch. I move it here, and I've got J here. Fantastic. I couldn't do this on the blackboard. So yeah, now I can describe the intersections of McNamara cells with double Iwahori sets, and they correspond to the states of color lattice models now. Again, I don't know the weights, I don't do anything. I mean, I just look at the geometry of the decomposition corresponding to my Whittaker function, and it just gives me the right objects. It gives me the right things. So second, my second result is that I introduced the colored loot-stick data. Let me show you. Colored loot-stick data. This is just refinement of the loot-stick data that we had before. I introduced colored Gelfand settling patterns, which is very similar. It is another combinatorial data. I describe them purely combinatorically. You can use them without, reference to any of this business. It is just combinatorial object. And I showed that there is weight preserving bijection between all of this. So you can actually describe something in terms of colored loot-stick data, in terms of Gelfand settling patterns, and in terms of the solvable lattice models with colors. So all of this data is essentially the same. Pretty much as before, but now we have colors. It is way more refined version. And finally, the third one, the last one in this talk, is that my Iwahori-Whittaker functions, these matrix coefficients and p-adic representations, these quite abstract objects, they are just sum over this data. You just, as before, as I show you in the example, you just fix the top, you just fix the output, the input, the output, and then you just consider all the possible things. You take the weights, you take the sum, you get the value of the Iwahori-Whittaker functions. And you can get this by the second result. You can get them not necessarily by using lattice model. You could use also Gelfand settling patterns. You could also use the loot-stick data. Oh, Alexei is asking fantastic question. Loot-stick data parameterizes basis vectors in the crystal basis that I was talking. What about this refinement? This is something that I'm actually studying right now, and I studied it slightly differently. How I think about that is, I told you before that Mirkovich-Vilonen cycles, they in bijection with these SMs. So there is some geometric subvarieties of affine Grassmannian, and these pieces are kind of the same, they're bijective. So now I'm thinking, what's going to happen if I take my intersections? I'm gonna use something like this. What's going to be here? It's going to be some subsets of Mirkovich-Vilonen cycles. So this is the part that I'm analyzing, and how it's related to what Alexei is asking. On the Mirkovich-Vilonen cycles, there is crystal structure. That's probably not clear for people who didn't work on that, but there is raising and lowering operators in terms of all these geometric subvarieties, and they have some combinatorial structure on them. And it turned out that the same structure holds for these McNamara cells. So this is what Peter proved. Now I want to get the refinement and try to understand what is the more fine version of the colored, of this colored loot-stick data. And I didn't get the answer yet. And this is something that I'm working actively on right now. So thank you for the question. It is literally, what I'm doing daily. I'm thinking about these questions. So this is refined new versions, and they definitely correspond to some geometric pieces which are natural, but I don't know about the crystal interpretation yet. It could be some de Mazur crystals, but if you fix one of the permutations, but I don't know the results yet. And let me spend the last minute on the possible questions. So I made everything for GLN. What about symplectic group or orthogonal groups or any other group, split reductive groups? The answer is this one is, kind of done. This one, I'm gonna do the dashed. This one is something I'm working on. And it seems like everything works as well. You describe something in terms of the integrals, you calculate the integrals, you get the weights, you describe the geometric pieces combinatorically. It takes some time, and I'm trying to finish my paper that I have already. So work in progress. And about the orthogonal, I didn't do anything yet. So I don't know. I hope, as I said in the very beginning, it's work in progress. I have a huge hope that it's going to work, but I didn't prove for every type yet. So this is the first question. The second, what about metaplastic covers? I was talking about the GLN itself, but there is a huge theory Hendrik was mentioning at the end of his talk, that there is also metaplastic covers. It is another refinement that you can get. And the result that I have is that there is versions of metaplastic combinatorial data, so you can just put new weights onto the very same things, and you can get to the. Okay, here I should be careful. I didn't write anything down, so I don't have any text to show you to support what I'm talking right now. But it feels from the calculations that I made is that if you carry the metaplastic group on the left, you're going to get symmetric color models that were introduced 2 months ago by 2 independent papers. So it seems like if you just do metaplastic thing, again, everything works by streamline. You don't need to guess weights. You just put everything on rails. It just goes on the left. It just goes up to until it hits the solvable lattice models. So this is the second question. Metaplastic covers, I don't know, in progress. And the third question is something that Ben and Valentin were asking about. Okay, Slava, you took some decomposition of U minus. What about some other decompositions? There could be other ways how you can decompose these things, etc., etc. So here there are two what people call good ones. And if you pick any of those, you have the combinatorial theory, you have the lattice models, everything, and they're different. It is different. Let me show you again this thing. You might notice that actually these lattice models, they turn on the left. It is because this calculation I made for another decomposition. So actually I have 2 decompositions and I have 2 lattice models, and they're not in bijection with each other. They're truly different. So you have lattice models that turn on the left, on the right, and it is not just reflection of one to another. So actually I have at least 2 combinatorial theory for the entire business that I'm talking about here. And I don't know what about arbitrary. I commented a bit on Valentin's question, what if you take arbitrary one, which are parameterized by the, as Dan is writing, that are parameterized by the decompositions of the lone whale word. But it's work in progress. There are lots of questions. So, and I end my talk. Sorry for taking so much time of yours. Thank you. Oh yeah, there is one question Alexei asked. Yes, indeed, the vertex states are also integrals of the corresponding geometric pieces. You can, when you calculate the integral, you're again going to have the decomposition into over the positive roots, and each of the vertices is going to be exactly the weight. So you again, actually everything works the same for the colored vertex as well. Okay, let me stop recording.